Again, remind me to do the recording. And now I'll do the share screen.
The students that are here don't have the right.
What?
The students that came to the lecture are not the ones to tell you to record. You need the ones that aren't here to remind you to record. We are here. We don't need the recording.
You may. Wait before the exam. Okay, so right now, today the plan is basically three. I'll see how it goes. So we have, I want to complete where were I? I want to complete the discussion we had about the basics of special relativity. And then I owe you a tutorial. This is the right place to put the tutorial. So I will put the tutorial rather than there was on Thursday. And then if we have time, then we will not waste it and proceed right away to discuss the next step, which is a basic introduction to the basic ingredients of the standard model. I'm not sure which is the right order. I mean, I'm sure that we're going to start with completing the discussion about special relativity, but then I'll see if we should continue a little bit with the standard model and then go to the tutorial or not. But in any case, today we will have a tutorial. As I told you, the tutorials I have are actually copied from the same course that was given in Tel Aviv. So we keep on to make sure that it's the same level and the same material that is being taught, both here and there. So it was kindly given to me by some guys in Tel Aviv. Okay, so let's start with a quick recap on what we did last time. So we began by basic discussions about particle physics, what is elementary particles, how to produce particles, how to detect particles, what is the framework in which we work on. We said that this is a quantum field theory, but I'm not assuming that you know quantum field theory. I will teach you bits and pieces of quantum field theory as needed. What we will have to have is the basic concepts, and that will go through in the course. And then we spoke about natural units. I will say a few words about that in the tutorial. And then we went to discuss special relativity. I'm doing some constructions around here. Okay, so we said that the basics of special relativity really begin with the Michelson and Morley experiment, which proved that the speed of light is the same for two observers that are in two inertial frames, even if these two frames are moving with respect to each other. And we said that there is a conserved quantity, which we call the interval. So the interval square is delta S squared is just C delta T squared minus delta X squared minus delta Y squared minus delta Z squared. And this is something which is conserved. That both observers in both in different frames would disagree on the location of an event, would disagree on the time in which the event took place, but both would agree on the interval between two events. Remember that the basic entity in relativity is an event. An event, a particle decays into two other particles that occur at a certain time, at a certain location. But event is something which is more general. Somebody scored a goal, this is an event. Okay. And we said that the interval has a very close analogy to the concept of distance in Euclidean geometry. And then we said that mainly a notation, any event is described by four quantities, one time and three of space. So we call it a four vector, call it x mu, which is x0, x1, x2, x3. Which is simply t, x, y, and z. This is a four vector. I told you that it is important to put the Greek index mu on top as an uppercase, not as a lowercase. And then we define a metric. In particle physics, it will always be G mu nu. Always, I mean, in all the textbooks that I have seen, they always call it G mu nu, but I call it eta mu nu. And those of you who will learn special relativity will understand exactly why I do that. So for you, it's the same right now, because in this course, we're not doing general relativity. So it is just a very simple matrix, zeros everywhere except at the diagonal. And we have a +1 and then 3 -1s. And I told you, quite importantly, to remember that this definition is opposite to the definition used in astrophysics and in general relativity. So G mu nu GR is -1 times G mu nu particles. Why? To confuse you. And then I said that with this new convention, I could define the interval delta S squared is just eta mu nu delta x mu delta x nu. And we use the Einstein summation convention when every time we're seeing an index that appears twice, once as an upper index and once as a lower index, we assume that there is a summation here. But since they appear once as an upper index and once as a lower index, so we don't need to put the summation. We can simply ignore it. But if you're confused, then you put back the summation. Then we define the Lorentz transformation as a general, any transformation that conserves the interval. It's a linear transformation, actually. It has to be linear. It's a good point. This is a definition of a Lorentz transformation. And under this definition, we find that simple rotations in Euclidean space is a legitimate Lorentz transformation. I write it down with one upper index, one lower index. So there was a bit subtlety of notation because I told you that the frame S prime, I would write as x mu prime and not as x prime mu. So this is the notation that I'm using. But here it's a transformation matrix between two different frames. So I'm using lambda mu prime and then mu. It would make sense to have lambda prime mu nu. It has a different meaning. So we have lambda mu prime nu. So for rotation, this would be something like 1, 0, 0, 0, 0, 0, 0, 0, and then cosine theta, sine theta, and minus sine theta, cosine theta, 0, 0, 1, 0, 0. Well, it's a simple matrix. It's a rotation. I just added the time, right? If you're confused, then it's a time x, y, z. And then this way you can clearly see the mathematical structure of a Lorentz transformation. But the Lorentz transformation that is a bit more interesting to us is a transformation which involves rotation when time is one of the axes. And then we wrote it as lambda mu prime nu is just cosine hyperbolicus of phi, sine hyperbolicus of phi. Sorry, minus sine hyperbolicus, and then another minus sine hyperbolicus of phi, cosine hyperbolicus of phi, and then 1, 0, 0, 1. Phi is known as the rapidity. And in fact, as we show, we can identify, and phi goes from minus infinity to infinity. And then we can identify beta, which is V over C, as tangent hyperbolicus of phi. And then we end up with cosine hyperbolicus of phi, which is just gamma times beta, where gamma is just 1 over square root of 1 minus beta squared. And we retrieve back the familiar Lorentz transformation, lambda nu prime nu, which is gamma minus gamma beta minus gamma beta gamma. Which is what you're familiar with from first year studies, from the transformation between two frames and one is moving in the x direction with respect to the other. Of course, this is much more general. Then we discuss the scalar product of two vectors, 4 vectors. So we define a covector, B mu, so definition. We use the matrix to lower an index, it's G mu nu B nu. Of course, there is a summation here. But since G is so simple matrix, then it doesn't really cause us much of a trouble. And then the scalar product between any 2 4 vectors, A dot B, is just defined as A mu B mu. So it's A0 B0 minus A1 B1 minus A2 B2 minus A3 B3. Right, these are the components, right? A0, this is the zeroth component of the vector A. So in a Minkowski space, now of course the norm of a vector, right? A, the norm of a vector is just, or A squared, is just A dot A, right? The square of the norm of a vector. So in a Minkowski space, the norm of a vector can be 0 even if the vector itself is not 0. Right? And we said that if A squared is greater than 0, then we call A mu to be time-like. If it is equal to 0, we call it light-like. If it's smaller than 0, we call it space-like. Of course, we and all other particles, we live in a time-like world, because time for us progresses faster than space. And zero mass particles live in light. Well, the word line, I haven't defined a word line, I'm going to do it right away. There are hypothetical particles which were never seen, but can be envisioned to have a space-like, which is basically means that these particles travel faster than light. There is no any experimental evidence that such particles exist. You might have heard the name, it's called tachyons. There are their names in the popular literature. Okay, this is as far as we went to last time. So before I proceed with the new stuff, questions? Nobody? If you don't ask me any questions, then I'm assuming everything is clear. Now, for some of you, I'm sure everything is clear. For some others, I'm not 100% sure. Questions? For Those of you who are with cameras off, I cannot even see your faces, so I don't even know much. Okay, let's just go, take for granted a few things that you know, not take for granted, sorry. Just give you the basics. So the thing which is known as time dilation. Right? So, time is not the same for different observers, right? So if let's say that I'm observer O, and I'm at rest. I'm always at rest relative to myself, right? Even if you're seemingly moving, then I'm still at rest relative to me. So if I'm holding a clock, right, then the clock ticks, and the separation between the ticks, right? Holds the clock. So the separation between the ticks is delta x. What is that? What is the spatial separation between the ticks?
0.
0. I'm holding it with me, right? I can be moving, but relative to me, the clock is not moving at all, right? I'm not looking on the outside world. I can be flying right now in an airplane, but for me, the clock, is with me. So there's 0. And delta t is, we call it dt. This is the time that the manufacturer of the clock meant that it will have between any two clocks, right? This is the nominal period. Right? So this nominal period, it has a name. Do you know what's the name? If you took first year's special relativity, I'm sure you've heard the name. What's the name of this nominal period?
Proper time?
Proper time, very good. So this is called the proper time. So proper time is the time that the clock ticks in a frame which is not moving at all. Now I'm talking about clocks, but you can think of a particle, of a cosmic ray, right, that decays in the atmosphere. Now it may be seen to us as being moving very, very fast, right, close to the speed of light, which it really is relative to us. But from the point of view of the particle, it's not moving at all, right? So the proper time is denoted by d tau. This is the technical, just to discriminate between t and it's called tau, right? Now remember the definition of the interval, which we had above, right? So we can write down delta tau squared. I just want to make sure I haven't mixed the signs. No, I have not, I hope. This is just the interval divided by c. I'm still putting the c just to get you less confused. But as you know, natural unit c is equal to 1. So this is definition, right, of the interval. So this is just 1 over c squared and then g mu nu delta x mu delta x nu. Because this is the interval. Right? This is what we had here. I just wrote it down. Now we have a second observer, right, O prime, who's seeing me moving. So I'm carrying the clock with me. I'm sitting in a train and I'm moving, right? So a second observer, O prime, sees the clock moving at some velocity v. So according to U, you're assuming moving, right, or O prime, right? The two ticks are separated by delta T prime, but the space interval is also being separated, right, by delta X prime, which is just V delta T prime. Right, this is a separation between two ticks. So the proper time, delta tau prime, right, is just delta T prime squared minus delta X prime squared divided by C squared, 1/2. So just 1 minus beta squared, 1/2 times delta T prime, where I just put delta X prime is V times delta T prime. So I can take delta T prime outside of the parentheses. Now, both observers are in inertial coordinate systems, right? So the coordinate systems are related via Lorentz transformation. Which means what? We said that in a Lorentz transformation, the interval, both observers agree on the interval. And since the proper time is just the interval multiplied by a constant, then both observers agree on the proper time. So delta T tau is equal to delta tau prime which means that when the observer O prime sees the clock in motion, right, it sees it ticking with a period, which is delta T prime is just 1 minus beta squared minus 1/2 times delta T, right? Because delta tau is just delta T.
Asaf, just to verify that the difference between T and tau, tau is the entire interval. Instead of using S, you're now using tau, and T is just the time-like component of tau.
Tau is the proper time. T is the time-like component of the 4 vector that describe the coordinate of an event. Tau is the proper time. So it's the time-like component. If you want, you can think of it as the time-like component of a 4 vector that describes the event in the rest frame of the particle, in which the particle is not moving. However, this is a conserved quantity because the interval is conserved. So we call it a Lorentz invariant.
So tau is the time in the rest frame of the particle?
Yes.
So what is tau prime in that case?
Well, it's a mathematical entity which is conserved, right? We call it the interval. This is the definition, right? We said this is the definition of tau. Of the proper time. So if you want, you can think of it as the interval divided by a constant.
Right. Okay. So if that constant is equal to 1, it's the same thing.
Yeah, it's the same like the interval.
According to this equation, tau is not the time-like component. According to this equation, tau is the interval, including both.
Tau is the interval. That's true. Tau is the interval. It's equal. This is the interval. Sorry. Tau is the proper time. It is related to the interval by multiplicity of a constant.
Okay, which I can
now,
say
in natural units, it's the same units. In real life units, it has units of time because the interval has units of length, and we divide by c. So in regular units, it does have units of time, but you're right that in proper units, well, no, because it has the same units as the length, right? The units of energy to some power.
I'm just confused. I think you said at one point that tau is the time-like component, and then your equation in the green box claims that tau is not the time-like component, but is the entire interval. So
the component doesn't have intervals. It doesn't have component.
The definition is very clear here, right? Tau is a proper time, right? It is equal, to the nominal period that you'd have if you carry the clock with you. So for a clock which is at rest, carried by an observer at rest. It is a conserved quantity, right? Because by definition, it is related to the interval multiplied by a constant, 1 over c.
Okay, I see.
Okay, so two observers would agree on that. Now, t, as opposed to that, t is the time component of the 4 vector that describes the event or the particle.
I have a question. You're assuming that the O prime observer is traveling in the x direction, correct?
No, I'm assuming that the O prime observer is seeing me.
Oh.
He's seeing me. I'm carrying the clock. I'm the O observer.
Mm-hmm.
Now I'm moving. Okay, if there was a class, I could walk around in the class. Now I can walk around in my room, but it's not going to be very helpful because then I'll get out of the camera.
So,
but let's say that I'm moving. Okay, I'm walking. Now I'm carrying the clock with me. So when I look at the clock is not going anywhere. The clock is stick to my hand, right? Yes. With respect to me, the clock is not moving. Now you are watching me, and you say, "Oh, you are moving." Now in your frame,
he sees us moving.
Yeah, you're seeing me and my clock. We are both moving with respect to you.
And it's only on the x direction, you're assuming.
I didn't say where I'm moving. I mean, in this example, actually, no, even in this example, it's general enough.
Oh.
Okay, I put x, but it doesn't matter which direction.
No,
it's all symmetric, right? In x, y, and z.
Yes, but if we have it in other axes, will there be another, like a different thing for the, like another beta squared?
You have to calculate the velocity, right? If you have to add the velocity vectors. We're actually going to do that in the tutorial.
Okay.
Wait another 20 minutes and we'll do it in the tutorial. Okay, so this is equal, of course, 1 minus beta square minus 1/2 is just gamma, so it's just gamma delta t. Right, so from your perspective, since you're seeing me moving, you're seeing that my clock runs slower. This is the origin of the famous
the twin paradox.
The twin paradox. This is the famous of the origin of the twin paradox, right? Two twins, one go in a spaceship, travel to the nearest star for 10 years, go back. So he's 10 years older, 20, 10 years there, 10 years back, he's 20 years older. In the meantime, depending, of course, on the velocity that he travels, then his twin brother here feels that it's been much longer than 20 years, maybe 50 years, depending on the velocity of the astronaut. So one twin, if they left it when they were both 20, when he's back, he'll be 40, but his twin brother would be 70. The paradox, of course, is that from the point of view of the astronaut, he is not moving, but the Earth is moving. So he would expect his brother to stay younger. If you want to know the solution, go to the general relativity course and then you learn exactly what is the solution to that. But let's proceed because I'm spending a little bit more time than I actually planned on these things. I know it's fascinating, but this is more of a general relativity type of course. Okay, but I still need to do some things which you need to be clarified. Okay, so what I really was aiming to is to get into the kinematics, special relativity kinematics, because this is thing which we're going to use all the time in particle course. So special relativity kinematics. Okay, so that is, we want to describe the motion of particle in space-time. Okay, so motion of particle. Right. Now, in classical mechanics, also in quantum mechanics, right, we're used to think of the particle, describing a particle as the location as a function of time. Right, so x is x of t. Right, or in quantum mechanics, it will be the wave function that evolves as a function of time. Psi, right, is psi of t. Something happened, we write the Hamiltonian, and we know how to solve it. Now we can't do it in special relativity. Why not?
Time would be different for different
Because
observers.
time is one of the coordinates. It's not an independent, right? When you do it like that, you think of time as an independent entity. You're right, what you said, right? This is because we're used to think of time as something which is independent and things happen as time evolves. Now here, time is a dependent coordinate. So we can't really do it. So we think of the way to think of it is a space-time location of a particle. That's known as a world line. Now you might have seen that. So you draw this nice picture where you put all the space coordinates into one. So this will be the x, and all the time coordinates into the y-axis. So this will be ct. And then if you want to describe what happens to a particle, then you just draw a curve to the particle, right? So the time always progresses, right? How would I describe the motion of photons, for example?
Straight 45-degree line.
Okay, photons always travel the speed of light. So I can only describe them like that. That's, by the way, called the light cone, right? Everything here is a light cone. I cannot go outside here. And actually, the way I plotted it is quite bad. Because there is no way for me to get outside of the light cone because that requires me to travel faster than light. So I can only travel somewhere here. And this photon, this is me. Right, so this is called the world line. So if I want to describe my position or how my position changes, I just specify the coordinates. What did I do? Okay, good. I just specify my coordinates, right, along the world line. So to describe the motion, I have to specify x mu. Mu goes 0, 1, 2, 3 as a function of some parameter sigma along the world line. Right, so when sigma equal to 1, I'm here. When sigma equal to 2, I'm here, 3, etc. Now I wrote sigma just to emphasize that this is a general parameter along the world line. But what would be the most natural parameter to choose?
The interval?
Yeah, and closer to that, very close to that.
Proper time?
The proper time, of course. So normally what I write down is x mu of tau. So I describe the word line as a function of tau. And this is true for any massive particle. In fact, as we're going to see, I don't think we'll see it today, but we'll see it on Thursday. The whole concept of quantum field theory started from the requirement that nothing travels faster than light. So nothing crosses the. So we had to abandon the concept of action at a distance, which unknowingly you've been using that when you studied actually everything that you studied so far, unless you studied quantum field theory, right? How is the electromagnetic force acting, right? Particle is repelled by the electric field of others, but then you're assuming that somehow the momentum exchange happens at infinite speed, namely outside the light cone, so that can't happen. Okay, now the rest is actually quite straightforward, it's just a matter of definition. So we define the force velocity, right? U mu. How am I going to define it? Some clever idea?
The derivative of the 4 vector?
Yeah, with respect to what?
Proper time?
Of course. Very good. Now, again, similar to all other vectors, U mu is defined at any given location along the world line. Now remember that when we speak of d tau, right, d tau is just, d tau squared is 1 over c squared g mu nu delta x nu. So we have d tau is square root of dt squared minus dx squared over c squared, which is just dt times square root 1 minus dx over dt squared divided by c squared. So this is just dt times square root of 1 minus beta squared. So using that, we can write down the force velocity u0, right, dx me. What is x0? What is x0?
That's the time.
No, it's ct. So it's d ct over square root of 1 minus beta squared dt. Just c over square root of 1 minus beta squared. This is just gamma, so it's just gamma c. I'm still keeping the c just until you get used to it. Now, actually, until next lecture when I'm going to do proper particle physics, and then c is going to disappear. And then ui, the space components, just dxi over square root of 1 minus beta squared dt. So I can write this square root of 1 minus beta squared dxi over dt. So just gamma times vi, or gamma times beta I c. Again, I'm putting the c to help you get the idea, but it will be over. What is the norm of this for velocity? U is just G mu, right? U nu just G mu dx mu over the tau dx nu over the tau. Now I'm going to make use of that with the tau square. Okay, simply write it down as G mu nu dx nu over the tau squared. It'll be cheating, not too much. But this is just C squared, that's all. Okay, the next step again is quite straightforward. Now I can define the forward acceleration, right? Well, I'm going to define the forward acceleration, A nu.
For velocity derivative of vector of a proper time.
Of course, du mu over the tau. Thank you very much. And the force. Just m times A mu. It's just m times du mu over the tau. That's of course what comes instead of Newton's second law. Now, quite interestingly, it's very nice to show that the forward acceleration is always perpendicular to the forward velocity. It looks very strange at the beginning, right? A mu, u mu is just G mu right? du mu over the tau times u mu. But I can write it down as simply as 1/2 d G mu u mu over the tau. But this is just constant, right? This is just C squared. Right? But this is just the norm of u. So this is just 1/2 d of C squared over the tau, which is constant, which is 0, of course. It sounds a little bit strange at the beginning, but in reality, there is nothing too strange here. When you think a little bit of that some more, that simply means, each of these 4 vectors have 4 components. So it just means that the 4th component of A is not independent. It is dependent on the other 3 components. So that it conspires to end up with this vector being exactly perpendicular to the forward velocity. One of these mysteries of working in Minkowski space. Okay, the next is to speak about energy and momentum. And again, right now, things are going to be very straightforward once you get the basic concept. So how am I going to define the forward momentum?
MV velocity.
M times what?
For velocity.
Very good. M u mu, which is just m dx mu over the tau. What is the norm of the, well, you can immediately see that, right? So p squared, right, is just p mu, is just m squared c squared, p0 is just gamma mc, pi is just gamma beta I mc, or gamma vi. Yeah. Well, this is actually an exercise you're going to get to show what happens in the limit of small velocities. So I'm not going to do it right now. And we can take all that and get to the familiar relation. Just don't get confused. This is p squared, right? It's not the second component of p. This is p dot p, right? This is the zeroth component of p here, right? And this is the ith component of p, and this is p squared. It's not the second component. Of course, p0 is just e over c. This is something which you'll show at home. And this is just pi squared plus m squared c squared to the power 1/2. Which you get from here right away. Okay, I'm skipping some parts because we are sort of running out of time. And it's really cool, but it's not that crucial for particle physics. So there are some things here about photons, etc., but the idea is the same. Any questions?
Right, pi squared. You mean pi?
I'm sorry, I stopped hearing you.
Now can you hear me?
Yeah, I can hear you. Yeah, go on.
When you write pi squared,
yeah,
you sum over all i's, right?
Yes, of course. Yeah, of course. It's p1 squared plus p2 squared.
All right.
No, the only thing to be worried about is that here I'm using p squared. When I say p squared, then the meaning is the square of the norm of p. And not the second component of p, because when you write p and 2 with an upper index, that has a double meaning. So don't get confused. I mean, normally there is no particular reason for me to use the y component of the momentum, unless specified directly in the question. The normally p square means the square of the momentum. Okay, more questions. No? No, no. Okay. Just a few more bits and then we'll finish with that. So the mass of a composite system. So let's say we have a system that contains 2 particles, right? I have 2 momenta, so 2 particle system. So 2 momenta, P1 mu and P2 mu. Right, so the total mass, m squared, right? It's just P1 mu plus P2 mu squared times c squared, but at this point I'm just what's written here. I just remove the c squared. This is of course just E1 plus E2 squared minus P1 vector plus P2 vector squared. So when you open it up, this is just M1 squared plus M2 squared plus 2 E1 E2 minus 2 P1 dot P2. So in particle physics, mass is not conserved. The mass of a system is not equal to a simple summation of the masses of the 2 particles composing it. Right? the mass is not a simple sum of the two masses. This is not classical mechanics. However, we know that p squared, right? P mu. Why is it just E1 plus E2 squared minus P1 plus P2 squared, right? This is a scalar, and it is a Lorentz invariant. Right? So this has a Lorentz invariant means it has the same value in every reference frame, every inertial reference frame. You can read my handwriting. I'm still not used to writing on these tablets, but certainly better than without it, but it still kind of gives me a pretty bad handwriting. It's bad anyway, but I think this makes it even worse. If you cannot read something, then let me know, right? This has actually quite an important experimental meaning, because what we do in particle physics, we said we normally, how do we discover a new particle, right? You take a particle, let it decay, essentially, right, to other particles. So, if a particle decays into two particles, then this invariant mass, this is called the invariant mass. It's called invariant mass. Right. So if you have a particle that decays into two other particles, then the invariant mass is conserved. So in every frame. So, if you can measure the outcome, that could tell you what was the mass of the initial particle. And you can do it in any frame, so it doesn't matter. So, if we happen to know what is the mass of the parent particle, right, the particle that decays, and we are now measuring, some outcome of some experiment, and we add up the masses and we end up with the same invariant mass, then we can possibly argue that these particles came out of a decay of the particle whose mass is known. Right? Now, alternatively, we may want to find a new particle, right, whose mass is unknown. So, some people are doing these experiments, and they found they analyzed the outcome, and they found that there is a lot of many collection of many particles. But in all experiments, they all, when you sum up their invariant masses, they all give up roughly the same value. That's a quite good indication that whatever produced this shower of particles is a new particle of that mass. Okay, now just to make sure that you're with me, note the difference between invariant quantity and conserved quantity. Invariant means it has the same value in different frames, but it's not conserved. Conserved meaning that in an interaction, which can be viewed at one frame or can be viewed in another frame, but in a given interaction, it is the same. right? So mass is not like that. So it's an invariant, but it's not conserved. Momentum, for example, is not invariant, right? If you look at the component of the momentum in different frames, they have different components, but it is conserved in any interaction. All right, you with me?
So if I understand correctly, mass, you might see two light particles that become much heavier than the sum of their parts, but every observer will see the same mass, like the same two light particles becoming the same larger particle.
No. You can have, right? You can have a situation, that's what you do in colliders, right? You take two beams of particles, you collide them, and when they collide, you might create new particles, right? Now, the problem is often, if you can see the particle, that's great. The problem is often that you don't see the particle. You just see the decay product of the particle. So you're producing a particle, as we're going to show again, not today, but next on Thursday. Most of the particles, in fact, nearly all of them, except only very few, are actually unstable. That's why we don't see them in everyday life, right? Nearly all particles are unstable, and some of them, the lifetimes are extremely short. So you don't even see those in detectors. Sometimes you can see the traces. By the way, I asked you to read Griffith's chapter 1. Did you read it? Okay, you don't have to answer. Read
I
it.
think most of us did.
They show some really nice old experiments of bubble chambers where you actually can see the decay of your particles. And the problem is if you don't see it. So the answer is, going back to your question, right? So the answer is mass. So if you have a decay, then mass itself of a particle is not conserved, but the invariant mass, right, this p squared is conserved. So if you're looking at two particles and you just measure their masses, or you're saying, let's say, okay, I'm seeing a muon and electron, anti-muon electron or whatever, right? You know what is them, and I know these masses. And so, no, I mean, this is not the mass of the parent particle, because you need to also consider their momentum and energy.
Yes, but if I ask my friend who was moving at the time, if he saw that and compare numbers, will we have the same numbers?
Yes, you will agree that the invariant mass is the same.
I understand.
That's the meaning of Lorentz invariant. It's two people that are not in the same reference frame, and therefore they disagree on various, on the coordinates of an event, but they do agree on some invariant quantities, such as the interval between two events or such as the invariant mass. Okay, last thing, which is really a notation, because I am going to use it, so you should be familiar with that. And it is just called the covariant notation of derivatives. This is a notation that enables us to, after you get used to it, of course, it enables us to quickly see the transformation law under Lorentz transformation. Right? So the definition of a covariant for derivative is d mu. This is the way I write it. D with mu as a subscript. Again, pay attention to the vocation. Is also another way of writing it is d over dx and mu now as an superscript. This is just dt and nabla. So just dt dx, dy, dz. Right, d is a partial derivative. Right, that you're all familiar with. And dt is just d over dt, right? It's just a partial derivative with respect to time. So you'll often see me using that. Possibly I might not even notice that I'm using that, because once you get used to it, it gets very, very handy and easy to use. And that's what it means. Now there is also a contravariant derivative. So it's with an uppercase, d mu, just d over d, and now x mu, x with a lowercase. Again, I did not have time because there is no real need in this course to get deep into the differences between vectors and co-vectors. I'll do the last advertisement and tell you that when you, those of you who come to the second semester's GR course will learn exactly all about that and why we need both of them. But here we just use them, and there's no need to go deep into why. It's just dt and then a minus, blah, blah. So this is just dt minus d over dx, not dt, d over dt, minus d over dy, and minus dz. Let's read a definition. So you'll see me using that. And once you get used to that, it will be very simple, natural, and straightforward. Questions? Questions. Okay, so as promised, right now, I'm not going to continue to the next subject, but I'm going to stop now and do a tutorial. Actually, have less time than I expected, so I'll do the tutorial now. And if needed, you see that we're running out of time, then we might simply continue with the tutorial first thing Thursday and then proceed with the regular lecture. Do you want to take a few minutes break, or do you want to continue straight on to the tutorial?
Maybe let's take 5 minutes.
Sorry?
Maybe let's take 5 minutes.
Okay, take 5 minutes.
Yeah.
So we meet here at, I'm leaving it open, but we meet here at 11:10 my clock. Now it's 11:05 my clock. So we meet here at 11:10 my clock for the tutorial session.
What velocity is your clock at?
What?
What velocity is your clock?
What velocity is my clock? Very good question. Very good question. We meet here at 11:10 my clock, which you'll have to guess which velocity it is moving relative to you, and continue the discussion and then do a tutorial. But since I'm staying here, then you can still ask me any question. Otherwise, I will look at the 14 emails that accumulated since the beginning of the last lecture in my mailbox.
That's an impressive rate.
What?
That's a very impressive rate.
That's a standard rate. That's only because right now it's too early in the US. It's unbelievable. I'm spending 30% of my time reading mails. It's just unbelievable. Okay, I'm going to take a cup of water and I'll be back. Okay, are we back? We back? Everybody back here? It's at 11:10 my clock. My clock says it's 11:10. All right, so we're going to begin our tutorial. Tutorial 1. And the tutorial now will be about natural units and relativistic kinematics. Of course, ideally, there should be a tutor, but there is no tutor, so I'm the tutor. Again, I do ask everybody who can to please open your cameras. That is really helpful for me. So let's begin with natural units. I said that in high energy physics, we use two fundamental constants, right? H bar is h over 2 pi, 1 over 0.66 times 10 to the minus 34, joule times second. So really it has units of mass times length squared divided by time. And then C, it's going to write it 3 times 10 to the 8 meters per second. First units of length over time. And we choose to work with H bar equal to C Also, in electrostatics and magnetostatics, right, we have epsilon zero, the vacuum permittivity and permeability. So we have epsilon zero equal to mu zero, they're all equal to 1. These are the units that we work on, that we work with. Now, it was a question that I was asked last time, right? When we require numerical results, we have to go back and do the dimensional analysis and multiply by the proper combination of H bar and C. So when we require numerical results, numerical results, then we perform dimensional analysis. Right, and multiply by the proper units, by the proper combination. Of H bar and C. Right, that's quite kind of easy. So for the energy, the units that we use are electron volts. Use electron volt. I already told you it's really GeV, giga electron volt. And of course, what is 1 electron volt? What's the definition?
The energy that an electron gets after going through a voltage of 1 volt.
Exactly. Electron, the definition. This is the kinetic energy, basically, of a particle with an electric mass and charge. So of an electron when under electric potential of 1 volt, when subject to an electric potential (1 volt). Of course, it's sort of an arbitrary. So if you compare that to the other units that you're used to in MKS system, so it's joules, so 1 electron volt is 1.6 times 10 to the minus 19 joule. And as we stated, in natural units, we derived that in class, right? We have energy, momentum, and mass. They all have units of electron volts. On the other hand, length and time both have the same units of electron volts to the minus 1. Okay, so now question. Question 1. What is H bar dot C in ordinary units? B. What is 1 femtometer in natural units? C. Find the period of a wave function of a free particle with a mass of 1 GeV in natural units. In the particle's rest frame. Okay, you want to try to do it by yourself, or shall we do it together straight away? Okay, let's solve it. So what is H bar C? What is H bar?
One point 1.066 times 10 to the minus 34.
5 or 6. 5, 4, I think. Check it out, plus 10 to the minus 34, but this is in joule per second. And we need to convert it to ordinary units.
I think that's joules second, not joules per second.
Okay. Well, what I would do, I would divide it by 1.6 times 10 to the minus 19. That's joules. That's ergs per joule per electron volt. And that is multiplied by 3 times 10 to the 8 meter per second. So when you collect the numbers, this gives you something like 2 times 10 to the minus 7 electron volt times meter. But I want to work with units of GeV. And I told you that the natural units of length, what is that in particle physics?
Femtometers.
It's femtometer, right? It's the size of a proton. So this gives us something like 0.2 GeV times femtometer. So that's actually turned out to be quite very useful relation to convert switch from natural to ordinary units. So it's something which is worth reminding, and it's also of the ordered one, like H or C is 0.2 GeV times femtometer. Every time you want to convert something to something else, to something simply something that's very easy to remember.
Note you wrote H bar as joules per second instead of joules times seconds.
That's because I made a mistake. Actually, I wrote it properly in my note, so the mistake happened now. Of course, the second cancel out. Thank you. Okay, so this is the that's very handy. It's very handy relation to remember. Okay, part B. What is 1 femtometer in natural units? Okay, well, that's natural units for meters. We say is energy. So we need to know what is 1 femtometer. But we already see that H bar C is 0.2 GeV times femtometer. So we can write down that 1 femtometer is just H bar C divided by 0.2 GeV. but h bar c is just 1. So it's just 1 over 0.2 GeV. So it's just 5 GeV minus 1. All right. So again, you see that these things kind of very nicely match into numbers that are of the order of unity when we speak about GeVs and femtometers. Okay, in part C of the question, find the period of a wave function of a free particle with a mass of 1 GeV in natural units in the particle's rest frame. So the wave function of the particle psi, right, is proportional to E minus IE or ET, right? But if we go to ordinary units, so in ordinary units, then we have psi goes E minus IE over H bar T. So if we ask for the periodicity, right, what is the period here? What is the period time? Is obtained
E over H bar?
Well, yeah, it's when E T over H bar equal to 2 pi. Right? So T is just 2 pi H bar divided by E. It's 2 pi H bar divided by MC squared, because we're in the particle's rest frame. So it's 2 pi times 1.055 times 10 to the minus 34 joule times second. And divided by, well, I just write it down as 1 GeV. Because I said that the particle's mass is 1 GeV. So now I need to get back the conversion. So it's 2 pi times 1.055 times 10 to the minus 34 joules times second divided by 1.6 times 10 to the minus 19 joules per electron volt times 1 GeV. So this gives me 2 pi times, okay, I did the conversion to GeV already. So 6.6 times 10 to the minus 25 GeV divided GeV times second divided by 1 GeV. So it's about 4 times 10 to the minus 24 seconds. Quite short. All right, questions? You got the idea? But this is supposed to be tutorial, so I'm not supposed to be me. I'm supposed to be the tutor, which is supposed to feel much more comfortable asking questions to.
In natural units, wouldn't it just be 2 pi over 1 GeV. So basically 2 pi GeV to the minus 1.
Actually, that's exactly. Yeah, actually, thinking of that. This is in seconds. And you're right that in time it will be 1 over, that's right. Okay. Yeah, you're right. We need to divide by, okay. Find out the relation in GeV. You're right. Thanks for pointing that out. This was in seconds, you're right. Okay. Now, relativity. So I'm not going to do the repetition because I think it's too fresh in your mind right now. But let's go straight to question number 2 about relativity. So the question goes like that. A proton is traveling at beta of 0.758 in the lab frame. So find the proton's energy and momentum in the lab frame. And B is find the proton energy and momentum in a frame S prime that is moving at velocity u of 80% the speed of light in a direction perpendicular to the proton's velocity in the lab frame. And the third part is to calculate the proton's mass in the frame S prime to explicitly show that it is invariant under Lorentz transformation. Okay. So how do we approach this problem?
Lorentz over and over.
Oh, so many Lorentzes. Okay, so first thing, solution. And so the first thing is that that you should be able to see it, but I'm not supposed to right now. We're going to use the known rest mass of the proton. So the known mass of the proton, which is something which you can find in Google, but what you should go to look for is a place called PDG. It's called Particle Data Group. And I'll send you their occasions. So the mass of the proton is 938 MeV. It's nearly 1 GeV. It's not a coincidence, of course. So without loss of generality, and in order to save us a lot of trouble, we're going to assume that the proton will be moving in the y direction and that the S prime frame is going to be moving in the x direction. Right? Because we were told that in the lab frame, the motion of S prime is perpendicular to the motion of the proton. Right? So we just assume that in the lab frame, this is the proton direction, and this is S prime direction. This is just you watching all that. So what is the form momentum of the, so now let's start that. What is the proton form momentum in the lab frame? So part A is quite simple, right? I'm just telling you there is a proton. The proton is traveling at some speed, which is cannot be neglected with respect to the speed of light, right? Beta is V over C. Find proton's energy and momentum. So what is the proton's energy?
Gamma MC squared. Huh? Now there is no C squared because I already used the mass with units of energy. Right? The mass already contains the units of energy, so there is no C squared here. And what are the units of gamma? Unitless.
Oh, sorry, the dimension. Yeah, the unit. What is the, sorry? It's dimensionless, right? Gamma and beta are dimensionless, right? Beta is V over C. So it's dimensionless. And gamma is 1 over square root 1 over minus beta squared. So it's also dimensionless. So we already have the dimensions. So E is just gamma times M0. So just down square root of 1 minus beta squared, 1.758 squared. So you can take your pocket calculator and find out that, if I'm not mistaken, because I did that to find a small typo, it's 1,438 MeV. This is the energy that we'll see, that we'll measure. What is the momentum of the proton? One at a time. Okay, what is the momentum in the x direction? Thank you. What is the momentum in the y direction?
Gamma MV.
And in the natural units that I'm using right now, is gamma mv, right? But it's gamma m beta, right? Normalized velocity. Right, I'm already using mass in units of energy. Why is the momentum in the z direction?
Zero. Aren't we assuming it's only in the
Zero,
y?
right? Proton is moving in the y direction. You just said that. That's we plotted here. So it is zero. So the only non-zero component of the momentum, well, this is momentum. Remember proton here. So the only non-zero component of the momentum is in the y direction, and this is just gamma times m0 times beta. Gamma times m0 is 438, so it's just 438 times beta, which is 0.758, so it's 1090 MeV in the y direction. Okay, let's do part B. So now in part B, you're asked, find the proton's energy and momentum in the frame S prime that is moving at speed of 0.8 p in a direction perpendicular to the proton's velocity in the lab frame. So here it's in the x direction. So what do we need to do? By the way, as you've seen in part A, there was no Lorentz transformation involved, right? Just the use of the energy and momentum definition. Now let's do part B. What do we do in part B? Now we do need to make a Lorentz transformation, right?
You write the matrix and then multiply it by the solution from A.
Right. So what is the energy in the S prime frame? Right. Well, the way I do it, I just remember it by heart. I do gamma minus gamma beta minus gamma beta gamma 0, 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 0. Times E, Px, Py, Pz. E prime, Px prime, Py prime, Pz prime. So what is E prime? You have to be careful here because this should be not writing. This is the transformation of the. Okay, it is a capital gamma. To discriminate between the proton, I said that the proton velocity is beta, and its Lorentz factor is gamma. So gamma in U would be the velocity and the Lorentz factor of the frame, of the U prime frame, the S prime frame. And gamma is just square root of 1 minus U squared. So what is E prime? What is the energy?
Gamma E.
Well, yeah, so we can say, let's write it down here, right? So E prime is just gamma times E minus U Px, right? This is the formula that you get, right? You're just multiplying a matrix and a vector, this is what you get. What is Px? Guys, what is Px?
Minus gamma UE.
No.
Px.
Zero.
Zero.
Zero, right? This is the proton momentum in the x direction as seen in the lab frame. And this is, again, this is the protons for momentum in the lab frame. This is the protons for momentum. Momentum in the S prime frame. Right, and we calculated the full momentum in the lab frame. Here it is in port A. Okay. So Px is 0. And what is gamma?
Five-thirds.
Not bad. Square root of 1 minus 0.8 squared. Indeed, 5/3. Times, we said E is 1438 MeV minus 0.8 times 0. So you end up with 2396 MeV. What is Px prime?
Minus gamma UE.
So gamma, right? Px minus UE. You all see that? It just follows from the matrix multiplying the 4 vector. So this is just square root of 1 minus 0.8 squared, and then we have 0, and then we have minus 0.8 times 1438 MeV, which is minus 1917 MeV. What is the momentum in the y direction? Py prime. So the momentum in the y direction is measured in the S prime frame.
Just Py.
It's the same. These haven't changed. That's right. Right. You can see it's here. It's moving in the x direction. So this is just 1090 MeV. And what is Z? The momentum in the Z direction? Oh, I'm running out of time. What is the momentum in the Z direction?
0.
Exactly. Now for part C. How do I calculate the invariant mass? The part C was calculate the proton's mass in the frame S prime to explicitly show that it is invariant under Lorentz transformation. So what is the invariant mass?
E squared minus P squared.
Very good. So M0 squared is just E squared. So it will be E prime squared minus P prime squared. So it's just 2396 squared minus, what did I do? 1917 squared minus 1090 squared, which according to my calculation, which you should check, is 877824 MeV squared, from which you get that M0 is, I got 9036.9 MeV. which is about 138 anyway. With some rounding errors. Check it out. Okay, I took a little bit too long of your time, so I should stop here. I will post down homework. You'll have until next Thursday for the homework. And I will post, at a certain time, I'll try to put some of my lecture notes online so you can see them. Questions before we end up this meeting? Any questions? Okay, as usual, it's not very difficult after you get used to it, but of course, if it's the first time you're doing this kind of thing, it takes a little bit of time to adjust. Don't feel too bad. It's not something that is that difficult. At least not to my opinion, but just get used to it. Any questions? Okay. You insist on not asking me any questions, then we'll see how well you're doing in the homework. Then we see each other again on Thursday, I believe. Alrighty.
Bye. Thank you very much.
Right.
Bye.
Thank you. תודה רבה.
Thank you very much.
Stop recording.